Lizbeth Shaid Sandoval Miranda. The talk is A-band sequences in categories as a read.
First of all, thank you so much for letting me give this talk. My talk is going to be a kind of mix between Spanish and English. So sorry if sometimes I speak in Spanish or I speak in English. These slides are written in English. So the purpose of this talk is talk about almost split sequences or Auslander-Rayton sequences and the Auslander-Rayton theory relative to a subcategory. Well, it's not for any subcategory of any category. We will consider K-algebra, and we will consider the full category of finally generated modules. And once we consider this category, we will consider subcategories in this category. But at the end of this talk, I will mention some other context for other categories different to category of modules where Auslander-Rayton sequences have been studied. So first, I will give some preliminaries. This is just to remind us what is a K-algebra. We know that if you consider K a field and A a ring with identity, A is a K-algebra if as a over K is a vector space which satisfies these properties. And the common examples of these K-algebras are the ring of polynomials over a field K, the K-algebra of matrices, and the Kronecker algebra with this representation. K-algebras are a particular case of Artin algebra, so we have this definition. If you consider R a commutative ring, a lambda be also a ring, this tuple is an R algebra when this is phi from R to lambda is a morphism of rings, satisfying that the image of R is included in the center of the ring R. And when we can consider also Artin algebras when R is an Artin ring and lambda is a finally generated module over R with the induced structure by the chain of rings. So I will use this notation for the full subcategory or finally generated modules. In this theory for finally generated modules over K-algebra, this is one of the most important theorems to study these modules is the Krug-Remarque-Schmidt, which says that if you consider a module, finally generated module for a K-algebra or an Artin algebra, your module have a decomposition in a decomposable module in this way, and this decomposition is unique up to the chains of the indices. Yeah? Translations. And these kind of theorems have been noticed when you consider Krug-Schmidt categories, which is categories where your objects can be decomposable as a coproduct of indecomposable objects. So some things that are true for this category are also true for Krug-Schmidt categories. I will denote like int lambda, the class of all indecomposable lambda modules, which are finally generated lambda modules. And the theorem, the second theorem that is important in this theory is that for arcane algebras we have duality. This duality allows us consider projectives, and we will know that the dual is going to be an injective module, and if you have a kernel, the dual is going to be a co-kernel, and all is stable, all is true. Also, we know how to get this duality. So sometimes it's sorry. It's the injective hole of the top of the ring R. See? Sometimes when you consider the ring and factors from the radical, it's called the top of the ring. So this is interesting because when you consider, instead of any commutative ring R, if you consider a field algebraically closed, this is going to be again K, and then this duality is easier to use, to work. It's one of the reasons because it's sometimes, in some way, it's easier to work with K algebras over algebraically closed fields instead of an arbitrary ring or an arbitrary field. Yeah. We say that a morphism F from X to Y is a split epimorphism if, as we know, F factors the identity on Y factors from F. What this means this, and duality will have that split monomorphisms that sometimes is called sections and retractions. But this is another notation. These two definitions are important for us. So we say that a morphism F from X to Y is called Y almost split if it's not a split epimorphism, and any morphism from X to Y that is not a split epimorphism factors through F. Yeah? And duality, we have the left almost split morphism if it's not a split monomorphism, and any morphism from Y to X to C, sorry, that is not a split monomorphism factors through G. All these modules are finally generated. And examples, when we study rings and modules, we consider the inclusions for the radical for a projective in the composable projective module into P. This is an almost right almost split morphism. And also, if we consider I, and in the composable injective module, if we consider the canonical epimorphism from I to the quotient of I, so the circle of I, this is an example of left almost split morphisms. These two examples are important in this theory for examples and also work. In this theory, this is important. If we have that F is a right almost split morphism, it can be proved that Y is in the composable, and otherwise if F is left almost split, then X is also in the composable. And once we have these two concepts, we say that what is an almost split sequence or an arcane latent sequences. This is a sure exact sequence that satisfies that G is an almost split morphism and F is a right almost split morphisms, and this satisfies some properties. Morphisms, I will say that what it means to be minimal. In almost split sequences, G and F are left and right minimal morphisms. This means that for all morphism H from Y to Y, such that HG is equal to G, or F, H is equal to F, then H is an isomorphism. Morphisms are right minimal and almost split, or co-minimal right almost split morphisms, and we have the duality for the left side. Minimal right almost split and minimal left almost split morphisms exist for every decomposable module in this category, and their domains are codomains are unique up to isomorphisms. This is a result from Auslander-Rayten and Smalo, and this is important for the definition of Auslander-Rayten with the equivers. And we have this kind of theorems that we mentioned at the end of this talk for subcategories. If we consider C beyond the decomposable non-projective lambda module, then there is up to isomorphisms a unique, what it means be up to isomorphisms, almost split sequence which end in C, where tau C is the Auslander-Rayten translation. This is a process in this theory. And if we consider X beyond the decomposable non-injective lambda module, then there is up to isomorphism a unique almost split sequence. So in this theorem, we can notice that if we want to translate or relative to do an analogous to the subcategory, one of the things that we need to study almost split sequences is, first, we need some similar to the Auslander-Rayten translation, or to get something related to this. And also, in our category, we know that what it means to be non-projective. First, we have the definition, the classical definition of being projective, but we also have other equivalent conditions. For example, for a projective module, we know that if you have a sure exact sequence which ends in C, this splits in the category of modules. But what happens when you consider a subcategory? This is not necessarily true. That's why it's important, the concept of projective. And the other equivalence that we know is that the X from P to any other module is 0. For modules, we know that the first thing that I said, that the short sequence is splits, is equivalent to the condition on the X functor. Yeah? But in general, this is for subcategories, this is not necessarily true. So for subcategories, the part of being non-projective, in our case, for example, is going to be replaced by some property on the X functor. I will mention this. So first, I will talk about irreducible morphisms, which is also important. So if X and Y are finally generated modules, we say that F is irreducible if F is not a split monomorphism or a split epimorphism, and this condition, if there exists a module C and a morphism H and G such that F is equal to GH, then H is a split monomorphism or G is split epimorphisms. This is in this theory for the category of mod A. This is important, and when we use these examples, this property, for example, we will prove that I don't have here. It can be proved that when you consider the canonical projection, it's going to be also irreducible morphisms, and in order to prove that, in some part we use the property of the image. But when we take these definitions and properties to subcategories, one of the things that we need is that all of objects lives in this subcategory. So in order to prove that, you need that some kernels and some images lives in your subcategory. So these kind of definitions need to be reformulated, or we need some changes. Examples, I said every minimal left or right or most split morphisms is irreducible, and in the embedding, and I forgot to add the projection. Once we have irreducible morphisms, we have this theorem of decomposition. If you have C, V in a decomposable module, and Y a non-zero module, G is irreducible if and only if there exists a morphism G0 from G0 to Z, such that in the induced morphism, this one, is a minimal right almost split morphisms, and we have duality. So these kind of terms can be generalized to subcategories. If we have that this is a short set sequences, it can prove, this was proved by Auslander, Reiten, and Smalo in 1995, that this is an almost split sequence if and only if F and G are both irreducible. That's why we can construct the Auslander, Reiten quiver, and this we can have this kind of properties. We'll mention this. And once we have irreducible morphisms, another thing is the radical. So if we have X and Y finally generated modules, we have the radical of X and Y such that the set of all F morphisms from X to Y such that for every module M and morphism H from N to X and H prime from Y to N, this composition is not an isomorphism. And it can prove these properties that if X is indecomposable, then the ring N of endomorphisms over X is local, and this is the Jacobson radical in the classical way. If X is indecomposable, we have that the radical from X to Y is exactly the morphisms which are not split mono duality. If Y is indecomposable, the radical from X to Y are the morphisms which are not split epimorphisms. This is saying that the radical is a subfunctor of the home, and once we have the radical 1, this can be generalized to the radical N in this way, for n greater than 2, f is in rad n from x to y. If and only if any of the following equivalence satisfies, that there exists a family of modules and a family of morphisms in the radical from x to ni, such that we can write f like this sum. This is important when we construct a standard rating quiver. And we have the infinite radical, which is defined like the intersection of all the radicals. We have some properties like this one. This is canonical properties that can be proved. This lemma says that if x and y are modules, which lambda is an Artin algebra, it can be proved that there exists a natural number n, such that the infinite radical is exactly the radical of n. And one of the main theorems is this one, made by Raimundo Bautista in 1980, which gave us an equivalence between the fact to be irreducible and conditions on the radicals. This is important, so you can prove that your morphism is irreducible if and only if it's in the radical but not in the second radical. Yeah? We have this descending chain. And we need this to remind this. If you have an Artin algebra, it's said to be a finite representation type or finite type if there exists only a finitely many isomorphism classes of indecomposable modules. And this is the canonical example. Well, the point is that by Kurzschmidt, it's clear that for representation finite algebra, we have complete knowledge of its representation theory once we have constructed a complete finite set of indecomposable modules, even if it's not easy to get it. So for an Artin algebra which finite type is computed that is equivalent, that for each B module finally generated, there exists some n natural number such that this punctor is 0, the rad from n 0, and the dual is also true. The dual is, the other side is also 0. So this gave us a connection to prove properties of the algebra through the radical. And a question in this part is that suppose that you have a family of morphisms from xi to xi plus 1 irreducibles between indecomposable modules. The question is when this composition is in the radical n plus 1. So these kind of questions have developed works made by Claudia Chayo and Sonia Trepode and other researchers. So a partial solution was given by Gusa and Todorov, and they proved that if you have K be an algebraically closed field and A be a finite K algebra, if you have a family of reducible morphisms between the composable modules, which satisfies some condition. I will not mention this. This is a definition. Then the compositions is in the radical of n, but not in the radical n plus 1. So we have an implication. And you can notice that this is a kind of generalization of the Bautista theorem. Okay. So, well, in order to study this, Shipping Liu introduced the grade of a irreducible morphism. So, if we have a morphism from x to y, we know this, right? We know that you have an induced morphism. So once you have this, you can consider the restriction on the radical. So you can consider these morphisms for the radical. And this induced in the category of functor from the mod up to abelian groups. This diagram. So you are going to the radical from n plus 1, from n plus 2, from x to y, and from the radical from n to n plus 1 to the x to y. Well, we have this diagram. So this let us to notice that if we consider f here, if g is here in this quotient, then it can prove that this composition is again in this quotient, and using properties of the kernel, it can be induced this morphism from the rad n module rad n plus 1 to rad n plus 1 to rad n plus 2. Yeah. So Shipping Liu in 92 defined the grade left and right for a reducible morphism. So it's in this way. So if you have f from irreducible, you say that the left degree of f is defined as follows. It's infinitive if for every n these morphisms induced is monomorphism, and if not, you consider m if there exists k in n such that here should be, instead of n is k, such that LKF is not a monomorphism, and m is the less natural number which is that property. So it can prove that if you have f, if a irreducible morphism, then the left degree of f is infinitive if and only if for every module C and for every morphism G in the radical n minus n but not n plus 1, it satisfies that the composition is not in the radical n plus 2. And this is the opposite. The degree of f is m if and only if m is the less natural number k, satisfying that there exists a module such that anamorphism G, such that this composition is the radical n plus 2. Yeah? So some of the times the left degree is not equal to the right degree. It can prove. So if we have that x is in the composable module in mod R, if H is a morphism from x to y, and irreducible morphisms, the degree or the left degree and the right degree duality is at least 1. And for an almost split sequence, it can prove that the degree of G and the degree of R is equal to 1. And also this is also true. If you have a morphism, we have been considered irreducible morphisms. We say that F is surjective and right minimal almost split, then the left degree of F is equal to 1 and the duality result. If F is injective morphisms and left right minimal almost split, then the right degree is also 1. So GPU characterize the irreducible morphisms with left degree 1, proving that given a reducible morphisms, the degree is 1 if and only if F is a surjective right minimal almost split morphism. So this result has been essential to achieve results when the decomposition of two reducible morphisms is a morphism non-zero in the radical 2. Yep. And he introduced some conditions, the sectional path and sectional path, because this is a technique to study irreducible morphisms in the land the Rayten quiver. This is the result by Chayo, Platica, and Trepol. It's interesting that when you have an Artin algebra, when the outlander Rayten quiver satisfies some special condition, for a reducible morphism, you get some equivalent conditions in order that the degree of left of F is finite in terms of the radical and in terms of the kernel. So this means that the kernel is in this component of the outlander Rayten quiver. There are more results, but it can prove that in this theorem, it's important the fact that you are working with algebraically closed fields. They have proved these conditions, but not in general. They have proved that the left degree of irreducible morphisms is finite if and only if there exists a positive integer and a morphism such that the composition is 0. So we have the equivalence. Well, they have proved more results in this idea. So all of these theorems can be generalized or relativizar, no sé cómo decirlo en inglés, relativizar, to subcategories or other categories with some conditions. So to summarize, the study of reducible morphisms and radicals, which is important in the outlander Rayten theory, has been amply treated in many contexts. And I have here, for examples, first, that, for example, Gladys Shalom and Hector Merklen introduced a study of reducible morphisms in subcategories, not only for modules, finite generated modules over a K-algebra, but also for subcategories of Krug-Schmidt categories. But when you read this paper, they mention that some results you can think like if you were working with modules. The second is Matthias Krebs in his PhD thesis made a study of reducible morphisms and introduced the study of degree in the context of the outlander Rayten theory relative to functorially resolving subcategories following the Chip-in-Liu work. And also Isabel Prati she gave a study of the degree of irreducible morphisms in the category of complex over projectives, where H is a hereditary algebra. And finally, this is a very interesting paper. Here, Shipping Liu and Charles Plaquet have studied Auslander latent theory, almost split sequences, but in a more general way. For exact categories and other contexts, exact categories are more generally than abelian categories. Well, given X as subcategory of mod A, we can notice that when we work in a subcategory on mod A, we are assuming that it's closed on the direct summas, is closed on the products, and we also consider that the indecomposable objects in this subcategory are exactly the indecomposable objects in mod lambda, which are in X. We are not considered different. The definitions that I said before to be irreducible is similar, so we are saying the same. The only thing that we need is that X and Y lives in X. It can prove in a similar way that if F is X irreducible morphism, then F is right minimal and F minimal, where this definition of minimal is the same. And the case, as in the case of mod lambda, is define the X radical in the same way, in a similar way. The point is that all of objects which are living in X and C is indecomposable in X, but we are using the same ideas. And it can prove also that if X is a morphism in X, if F, then F is X irreducible if and only if F lives in the radical X, but not in the radical to X. This is the generalization of the Bautista result. In this context, an X irreducible is not epimorphism or monomorphism, because the point is that our image or our kernel are not living in X necessarily. So that's the point, that in order to work, we cannot choose these properties like in the classical way. So it's necessary to include extra hypotheses to get the same, not same but similar, and also the framework of observation theory in subcategories. So when you consider X, the whole subcategory, you get the same. As you remember, when we worked, when we mentioned almost explicit sequence, we talked about the Auslander translation for A and C respectively. So for a subcategory, it's necessary to prove if these almost split sequences exist or not in that subcategory. In this case, for functorally finite, the existence of almost exact sequence in X was proved by Auslander and Smalo in 80. So this is important to study Auslander theory. And finally, we remember that given a module C, a morphism F is a left X approximation of X if every morphism from C to A, which with A in X, factors of F, and similar we have the left A approximation. Once we have this one, we can consider the minimal F approximation, and we say that a right X approximation of C is introduced in relative way, and we say that X is a covariant finite category if every module has a left X approximation, and duality X is a contravariantly finite category if every module in mod lambda has a right X approximation, and if this category is satisfied being covariantly or contravariantly, we say that it's functorially finite, and if satisfying just one, we say that it's homologically finite. Sorry. Well, this is one of the important results that I want to mention. Suppose that X is a contravariantly finite and extension closed. Then, according to this theorem by Kleiner, X has almost a split sequence on the right and left. For an almost split sequence, we have this property. We have that this is an almost split sequence in X where it can get what is exactly A, and we have this property that the X from C to Y is 0. If you notice, we are not saying this idea of being projective or non-projective. We have a similar idea in terms of the X. This extends the main result of Auslander and Smalo from 1981. And functorially finite and extension closed subcategory has almost split sequences. This generalized that result. And also, he resolved some questions made by Auslander and Smalo about the characterization of almost split sequences in subcategories. In this paper with Efren Perez, Mark Kleiner improved these results, and they proved that that Y is X injective, and show how to compute F and G. And if you remember the previous slices, when we consider an almost split sequence, we have that some modules are indecomposable, but here we don't have that property. So it depends on the subcategory. Thank you.
Any questions?
This radical functor, it's like the X and the term that have nice properties, and you have them, and you can do homology and this kind of things. The X, es que tenías el radical, ves que tienes una sucesión en cadenas. Entonces, cuando haces estas cadenas de radicales con un módulo fijo, tenías un cuadrito ahí, no me acuerdo si lo que se puede hacer es algo muy parecido a lo que hacen con
¿esto?
Ajá, ese tipo de cosas.
No lo he pensado. Lo que sí he notado es, por ejemplo, que ellos estudian, es por eso que lo pensé en poner más en un cuadrito, muchas cosas del grado, como lo trabajan en el carcaje de Auslander-Reiten, muchas veces es combinatoria, ¿no? Entonces es hacer contar. pero la parte más categórica de estudiar esto, que es decir, decidir cuándo este morfismo es mono o no, no ha sido estudiado, no ha sido muy estudiado, ¿no? En una manera más categórica.
No, yo lo que decía es, dados esos complejos de cadenas, o sea, porque seguramente puede
El radical.
¿se puede hacer alguna especie de homología?
No lo sé. Pero, por ejemplo, esta teoría que yo mencioné solo para subcategorías subcategorías de módulos finitamente generados sobre una álgebra, ya son estudiados en, por ejemplo, categorías exactas, categorías trianguladas y categorías que no son abelianas, no son las anteriores. Y en ese artículo que te digo que es de Shipping y Charles Paquet, o sea, ellos trabajan sobre eso y pues mencionan al inicio, ¿no? De que hay categorías donde ya saben cómo ciertas sucesiones de Auslander-Reiten vienen de otras, y a través de ciertos teoremas, ¿no? Por ejemplo, en estas que son subcategorías, o sea, no lo mencioné, pero tienen la subcategoría que satisface condiciones necesarias para que las cosas funcionen, tienen el traslado Auslander-Reiten, pero para obtener un trasladado ahí, pues lo que obtienen es que el módulo que están buscando es un sumando directo de la aproximación del módulo, porque lo que hacen las aproximaciones es que quizá tu módulo no vive en tu subcategoría, pero tú lo puedes buscar una aproximación, ¿no? Un módulo que vive en tu categoría y que cumple las condiciones que necesita, ¿no? Puedo decirlo de un modo muy burdo.
Any other question? We thank the speaker again.
Gracias.